Shall I start? I'm good. Okay, thanks, Stefan. Thank you, Stefan, for inviting me. And I think I wrote my abstract in a moment of mania when I thought I could write a talk covering 5 different topics at a time when I was also very solidly occupied by teaching in the previous few weeks. So this is going to be a bit bumpy, I think, but apologies for that. I thought I'd start with some classic Alan. This is the Dynamic Languages Symposium, after all. So this is a great way of putting something that I've also felt for a long time, that software it seems to somehow require more work than it should, right? I think that's something that many of us share. And one of the things that Alan Kay also likes to mention is this guy, Licklider, JCR Licklider, who was one of the early program managers at DARPA. And he was talking about how if we get this thing called the internet off the ground, then we're going to have this problem of bootstrapping communication between mutually unknowing parties, right? And that's essentially where I think the mess that I think Walter was talking about has really come from, in that this is only accelerating, right? The fact that we have more and more software arising from more and more disparate places and in more disparate forms, and it wants to talk to each piece wants to talk to each other. So this is my third, I'll stop doing quotes in a second, but this is my third quote, which I don't actually know who said this. It's another one that Alan Kay likes to come out with, but how programming is 95 or 99% glue code. Does anyone know who actually said this? I've been looking for a source and I don't know. It's probably just some meme that gets circulated. But my 20-year vision, coming back to Stefan's theme for the event, is how can we get past this problem? How can we stop this getting worse and actually make it get better? So I've actually been thinking about glue code quite a lot over my so-called career, and this is one piece of work that I've done, I suppose, fairly recently, along with a very good student, Guillaume Bertolon. And just to give you a little preview, this is Python code. It might not be completely obvious first. It's Python code, and all it's doing is it's using libpng, so PNG image decoding library, to read an image, and then later on, you can't quite see, but it displays the image on the screen. So your basic stuff using this library. But there's a little hint of what might be different about this, is that, well, we're calling a C function to start with. We just seem to call it in a fairly natural way, and it seems to work. And similarly, all these library functions are actually they're taken directly from libpng. And the sort of punchline a bit later will be that there isn't actually any glue code behind this. It's more that the implementation of Python has been written in a slightly different way that knows how to deal with these libraries. So the reason I think that dynamic languages have a potential to sort of combat glue code is that they have this very direct style, it's very flexible, and it's very usable. So what do I mean by that? Well, I mean that we can write something, doesn't really matter what the language is. Here I wrote x.y.foo, and I'm saying something very high level. I'm saying it in relatively little text. And this is the classic abstraction stuff. We've abstracted away a lot of details, so there'll be stuff about memory going on here that we've sort of hidden. So, it's a high level notation, right? Fair enough. But there's also something else that I think we don't remark very often, which is that we're being very flexible about what structures can go underneath that. So it's not just that there exists a concretion and we're abstracting away from that. It's also that there might be many, many different concretions, and they can all sit underneath this high-level intention, that there's an operation called foo associated with a data item called y that we get through a data item called x. So we can hide a lot of diversity underneath. And this is, I think, the same idea that the Jonathan Aldrich's essay from about 10 years ago about interoperability and why object orientation sort of lends itself to interoperability. It's the same idea. There can be many, many different concretions underneath each high-level intention. And indeed, the essence of late binding, people sometimes call it duck typing. I think it's something to do with typing. It's about binding. So it's about finding commonality where it exists. And dynamic languages are in a very good place with respect to this, because we've traded away a lot of stuff that make, if we want to have very strong ahead-of-time assurances using classic syntax-directed means, then we don't get this kind of heterogeneity and this kind of diversity. If you imagine doing, if you have some sort of Hindley-Milner type system, you end up with things like, lists have to be all the same type, and then, otherwise things break. So we've traded away that, and in return we've got a lot of flexibility. So we want to use that flexibility in a constructive way. And the final thing to observe is that the world is dynamic, right? So dynamic languages are almost tailor-made for for grappling with the diversity of the world outside the program, right? So we want to bring things in from the outside, we want to communicate with the outside. That's a world that respects relatively few invariants. A lot of things can change in the outside world, things can be very diverse. It's a large world, but it's an explorable world. So we like to interrogate the world, we like this fact that dynamic languages let us program exploratorily. And so maybe we shouldn't really talk about glue code at all, right? Maybe glue is sort of a disparaging term. We should talk about, integration or communication or something. But anyway, it feels like dynamic languages should let us perform these tasks that are interacting with a diverse outside world in a good way. And yet, this isn't how we implement dynamic languages at all, right? We still implement them as a closed box, and off you go. Your code goes here. Start now. You're going to enjoy being trapped in this box. So this is my metaphor for sort of the virtual machine paradigm of language implementation. And of course, we can make it slightly more comfortable. We can have nice standard libraries, but you're still, to some extent, trapped in a box. So the theme of what I've been trying to do with a lot of my work is trying to invert the box somehow. So make our code be something that exists that talks with the language being a window onto the world, right? So what if we weren't in a box, we didn't start with an empty box that says your code goes here, please enter some code. But actually we started with a view on a much bigger world, the world that is already out there, the world that already exists. So going back to my Python example, well, that happened to be an implementation of Python where all those libraries that were on my system were sort of immediately accessible in the Python environment. I didn't have to write that sort of binding code to make them available. Somehow the implementation had figured it out. Oh, there's the code again. That's what I want to show you. So how did it work in an outline? Well, we avoid writing this kind of thing. So this is one of the simpler sort of bits of C, Python C API code you might need to write. It's just wrapping a single one-argument function, which is the system function from the C library. But it's quite a high sort of noise-to-signal ratio. This is the same sort of topic that Walter was talking about. So what did I do instead? Well, the first step is to take a step back and say, what is our scope? And our scope is memory. So we've got an address space. Memory, it consists of a bunch of memory, and the memory has a structure to it. And this is a structure that is, it's outside our language implementation. It mostly comes sort of from the operating system. And what I did was build a runtime that basically understands what is in memory in a hierarchical sense. So we can divide up memory into a bunch of memory mappings. Underneath memory mappings, there might be, maybe this mapping is an arena for my malloc, and then I have a chunk in there. So the runtime is somehow, I won't go into details here, but it's somehow keeping track of what this structure is at all times in our address space. And the very leaves of this tree are the program variables, or you might have a malloc chunk, and then inside the chunk there's some one or more program values that we've stored there. So the leaves of the tree are somewhere where we can hang some kind of type information to say what those things actually mean. And then we can make it explorable by adding some kind of API for querying things like what's on the end of this pointer. So this is a project that I've been working on for quite some time now called liballocs, because it's all about viewing memory, an address space, as a collection of allocations that have various metadata associated with them, including types. Types in the sense of, well, a label saying something about how data is structured and what it means, not types in the Hindley-Milner sense or any other sort of static sense. So another kind of glue code that we might want to eliminate, not just code between languages, but it's actually code doing I/O, so code between my local view of data and some external view of data, like the format of a file that we might be storing or reading from. So this is just some code I stole from Stack Overflow, where someone's asking, how do I do file I/O in Python if my file looks like this? And the answer is, well, you write quite a significant amount of code to munge bits of strings and remove commas and things like this, which isn't really, again, commensurate to the task, right? The person had described their problem in just, an example and a sentence. And the answer was, well, write all this code that's actually pretty boring. So that's another sort of flavor of glue code that we should be able to eliminate. So doing this sort of thing, it feels like, yeah, there's definitely work we can do there. But what's the sort of deeper view, if any, on these ideas? And for a long time, I used to say that there's basically two paradigms of programming language, programming system implementation. One is the language virtual machine, which is kind of this closed box. Another is the tool chain with the linker, and then you can have many different sort of compilers that slot into that. But I've started to think that there might now be a third paradigm, which is actually much more outward-facing than the other two. I'm not sure how generally this works, right? So see what you think. So my first example of a really outward-facing programming system is Shell, right? The Unix shell. This happens to be possibly the earliest Unix shell that existed. This is Unix version 0, running on PDP 7, I think. Anyway, it's a really cool video. You should watch the video because it's really fun. Obviously, the shell is a programming language, but it is addressing the whole system image of the operating system, right? You've got the file system, it's got all your devices in it. It's very much facing outwards. So that seems like pretty useful, right? Pretty sort of, I actually find myself way more powerful from the shell than I do from a Python REPL, because there's so much more data that I can just directly manipulate, directly address, directly play with. Whereas with Python, I'm always worried about how do I import stuff, I've got to write all that code and so on. So something about the outward facingness of the shell is something that we can build on. Another kind of outward-facing programming system, it's a bit of a cheat really, but this is a machine monitor. This happens to be the Apple I machine monitor, right? So it's basically a little program that sits in your memory, and you can interactively inspect memory, and you can also it's basically got an assembly language REPL in it as well, so you can type in, you can enter little bits of code. And these were very common on early microcomputers. And the whole point of them was that there'd be stuff in your memory, let's say there'd be stuff in your ROM that you could mess with from this little REPL. So it wasn't that the REPL was giving you a closed environment. It was trying to expose the whole of the computer to you in a way that was interactive and sort of definitely outward facing. And my third example is debuggers, one of my favorite topics. So this is a silly little GDB session that I just did earlier, where it amused me to printf for some reason. And then I could evaluate an expression that was, calling the printf function and combining it, adding some value to it. And so inside the debugger, there is an implementation of the language. Here it happens to be C, it doesn't really matter. But it's a really, really wacky implementation. Right? It's completely separate from what's in C compiler. And it keeps almost no state of its own. Right? So when you tell it to evaluate this expression, it's looking in the program saying, okay, there's a thing called printf in there. We can look that up. And then we can, this variable x where we're storing our result is also just a program variable. So it's an implementation of the language that is entirely addressing the state that lives outside that implementation. I thought it was worth giving a plug to some other work that is even not very dynamic languagey, but it's definitely ticking this outward-facing box. So this is some F# code that's using this type providers thing. Right? So what is a type provider? Well, I think it's a bad name, really. It's not really essentially to do with types, but it's a way of saying, well, I've got some data in the outside world. So in this case, it's World Bank data. This is from Thomas Petrczak's paper, 2014. It happens because it's statically typed language. There's some staging going on where a little bit of code runs at compile time that will talk to the data source and generate some data types that are basically the main role of this type providers thing is to take features of a data set, like for example, you've got country codes, but they're just integers, right? They're just numbers, or you've got some sort of identifiers going on, and just to lift them up to the features of the language. So country codes don't exist in the abstraction that the programmer sees. Instead, there are countries that are named things in some sort of enumeration or abstract algebraic data type or whatever is appropriate. So this idea of lifting up features from external data into features of the language and doing it in a mechanized way is a really neat one, and it's one that I think dynamic languages could do even better than in something like this, where there are some sort of compile time versus runtime complexities to manage. And the final thing I wanted to sort of shout out to was, is Marcel here? No, maybe not. Anyway, so Marcel Weyer, he's got this Objective-S language that I think is really cool. So you can, it's very much a Smalltalk and Objective-C inspired language, but he has this feature called polymorphic identifiers. So the idea is that, well, normally program variables, we have a name for them, but actually we might have many namespaces, and some of them might be naming things that are completely outside the current program. And so it's a way of hiding the complexity, bringing those things in from the outside. So all of these things are things you can use in place of an ordinary identifier in your code. I happen not to like URLs very much. I think they're really ugly and not a very nice conceptual model anyway, but I'm quibbling. So this is a really nice feature, and it's definitely one more example of trying to bring the outside in a very direct way. So I don't have that much more to go. It's worth thinking a little bit about why is glue code necessary to bring data in from outside? And the reason I came up with is that inside our language implementation, we like to take control of how data is represented. So we say, well, objects look like this in my virtual machine, and they have a header, and the fields are either this or this or this, and this. So there's some very restrictive form that our data takes when it's inside our box, and that means obviously it's going to have to get translated to some other form when it's going in and out, right? So that's the basic bargain. And I sort of realized that it's a little bit like how you can think of this as a sort of an intermediate representation, right? We bring data in, and when we're working with it, it has this form that we control. But we always want to transform it from and to something else. So thinking by analogy a little bit with what the Truffle and Graal people are doing, and also the meta tracing strand of work, both of these are saying this intermediate representation thing, we don't actually need it. Right? We can just say, let's just write an interpreter, right? That's your definition of your language. Or describe the data you want to work with if we're talking about data. And then we can have some very clever dynamic compilation things that can basically do as well, not as well, but people are working on this, as we could when we actually siphoned everything through this quite restrictive intermediate representation. Because doing that siphoning is quite a lot of work for a lot of people. It limits the ease with which we can support new languages, or in my example, new data. So as a little anecdote of what that might mean for the internals of a language implementation, I showed you this Python thing that I've been working on. Well, there was an earlier iteration. In fact, there were two earlier iterations of that Python system. And the first one was a pretty conventional Python called Parathon. And it had this representation for, this is what a Parathon value looks like. So, values inside our runtime, they have this form, and they always have at least these 9 fields, and there's like 25 methods or whatever. So that's quite bulky. But anyway, and then in a later iteration, I realized that I could strip that all out. And I said, well, actually, there's no guaranteed representation of what's on the end if I pass you a pointer to these Parathon values, passing them around. But what I really mean is, there is some useful information in memory at that position. And I have a whole separate service that was like an earlier iteration of my liballocs memory querying service that I used to figure out how should we actually interact with this memory. So a sort of slightly more principled way of viewing that might be, what if we just said, we take some very wideband formalism for describing data, like a data description language. This snippet of code is from a data description language called DataScript that was created by Godmar Back about 20 years ago, and I tinkered with it a little bit during my PhD. And this snippet happens to be describing the Java class file format, which is a bit meta. It can basically describe any binary data up to some, it's embodying a sort of data-dependent grammar, so there's some limits on what structures it can recognize, but it can recognize an awful lot of structures. So in this scenario, we could say, well, analogous with our Truffle Graal thing, where we just care about interpreters of languages, can we just say we just care about working with data, and we have a very wideband notion of what that data is, and then can we build our virtual machines around that very accepting view of what the data is that they work with, and can we recover efficient access patterns using these clever dynamic compilation strategies analogous to what's been done in the space of interpreters. So that's my wild and crazy idea. I actually had an even more wild and crazy idea, which was, can we do the same thing for operations? So can we eliminate this idea of a built-in notion of what it means to do a call? That's even more. I've sketched some stuff out because it was fun, but that's even more crazy. So I'm not gonna dwell on that one. But it's a thought experiment that I've got intermittently ongoing, and it's really about what should the core of a language contain, right? If we think of building up a language in this vaguely meta-circular way, where we start from a core and we try and extend it, it's an interesting question about what should the core look like if we make an assumption that we want to embrace as wide a space of existing stuff out there in the world as we possibly can. Okay, I think that's everything I've got. So thank you very much for listening. You've been very quiet and respectful, which could be good or bad. So I'll take questions.
Who got a question for Stephen? Then let me start.
There was one from Andrew.
I'm curious to see type providers come up. I was expecting you to talk about that, but I see it as actually almost advocating for static types, because on one side you've got some kind of slightly unspecified data. Maybe it's got a schema or something, or it's an Excel spreadsheet or whatever. And on the other side, you've got a statically typed language F#, and you're basically bringing the outside world into this world where you've got invariants expressed by type. So I'm curious that you say that there's something for dynamic languages here. I always think of it as bringing dynamism into the statically typed world.
Yeah, what to say about that? I mean, I think the basic thing to observe is, if you try and think of the closest analogous thing, but in a dynamic language context, so let's say, what I want is data from a CSV file to be very naturally, idiomatically manipulable from whatever my host language environment is, then there's still a gap that can meaningfully be bridged there in the context of dynamic languages. So I wouldn't say that there's no value added by also having static typing on top of that. It's more that there is an analogous thing to be done there, and you could, this is me being very intuitive and hand-wavy, you could possibly do more by exploiting the fact that you have more freedom, but also fewer assurances, but more freedom in the dynamic language context. Yeah, that's about all.
Hello, Stephen. Thank you for an interesting talk. Can I ask you about whether you think components should be self-describing, or whether it's better to have some kind of omniscient description service that you query? That's one question. And the second one is, what are the security implications of being able to kind of hand an address to someone and say, tell me everything you know about this?
Okay, so the first question, is it better to have everything be self-describing or to rely on an omniscient external service? I think the latter, and the reason I say the latter is that if things are self-describing, then an omniscient service can just delegate back to the thing. But not everything in the world is self-describing, therefore one needs to have some, I mean, this is a very conceptual argument, right? That if not everything is self-describing, you're going to have a third party to talk to about the things that aren't. I don't know if I've grasped your question. Is that getting to it, Jeremy?
Yes, I think so.
Okay, thanks.
So you're accepting that there are some things that can't or don't describe themselves,
Yes,
I guess.
I think that's necessary.
Thank you. And how about security? Thank you.
Well, whether you can name something and whether you can access it, so I have to be careful what I say here, because I love capabilities. I think they're a great design, but I do seem to be working against them here. And I want to be able to say that naming something and accessing it are orthogonal. So there's both traditions exist, right? in the classic operating system case where you can have a single virtual address-based operating system, but different threads or processes have different access rights on the same piece of memory, right? So just being able to name something shouldn't mean that I necessarily have access to it. And I guess that is the model I have in mind with my stuff, rather than the capability one where we constrain the flow of names and therefore provide access control that way. But yeah.
Thank you.
Hi, interesting talk. I have two questions. First one is pretty simple. So I didn't really get your point for the first x.y foo example. So do you, that is the language you want, a kind of language in which you have a very strong type inference and you don't really have to write any types. Is that right understanding?
Yeah, so I'm imagining this being a dynamic language with no static type checking. But you're right that it could be, type inference could let you write something very similar.
Right. So, you can write x.y.foo even in Java, although in Java you have to write types. And the second question is, so I like your outside world example, but your outside world is still within a computer machine. But the real challenging thing is, the outside has to be, real world.
Sure. Well,
so how do you think about that?
Yeah. So I definitely, when I talk about the world, I intend to embrace not just the computer but the network. I just didn't have any examples of that in my slides, which is my bad. I suppose the closest I got was this file one, where we're talking about pushing data, and who knows where the data is actually going to end up. It could be a network file system, whatever. And then this idea that, at the very end, I was saying, well, what is a procedure call really, and how can we sort of how can we bootstrap a notion of interactions that is very general? Yeah, I'm not trying to stop at just the computer, but I suppose in terms of my work so far, I have done. So yeah, it wasn't the intention to limit the scope, but there's only so many things I can talk about. Yeah, good point.
So when you did the libpng in Python example that it looked quite natural, I wanted to ask about that because I didn't notice any area where you tell it to, for instance, load libpng. So does it just know all of the functions exported by all of the SOs on your entire system and load whichever shared object it needs to for that? Because that sounds like it could get complex quick and have potential, undesirable effects.
Sure, yeah.
With names.
I mistakenly left off. There is an import. Basically, you can import a native library very much like you import a Python library. The ideal is that they look exactly the same. I chopped that off in the name of eliminating noise, but now you mention it, it actually confused things, so I should have left it in. But yeah, it works the same.
That actually sounds quite good then. I was a bit worried before, but yeah.
Okay, just quickly, is Max here?
Yes, hi.
Great. Could you set up? So while you set up, one last question from me. I do really like the inside of the box. It's warm and fuzzy and nice. And the outside is really harsh and ugly, and I disagree with the design decisions. And is there some way to make it look nicer automatically, omnisciently, magically?
Yeah, I certainly think that we often when we're programming, we get hung up on making everything the same. And this could be something as simple as like coding style, where we say, oh, this project has this really stupid coding style where they use tabs, not spaces. Actually, I like tabs, but anyway, it doesn't matter. And for some reason, we tend not to invest in what are technically super feasible little mappings. We say, well, actually, I write in my style, and my editor converts it to the style that the remote project wants, and I never actually have to see that style. So there's a lot of really feasible, quite shallow transformations one could do, and I see the same issue coming up in the case of APIs and all this sort of whenever you import stuff from the outside, you really want to tailor it. But that tailoring needs to be done in a sort of rule-based way. It doesn't need to be, I explicitly code a wrapper for every function that I import, because that way lies madness. So getting this sort of rule-based adaptation thing going is, I think, one way to solve this problem, hopefully.
All right. Thanks, Stephen.